There we go. So yeah, like I just mentioned, we went through some of the PCAs or most of the PCA introduction stuff, but I did have a little notebook to kind of give a little bit of example of what like performing a PCA, principal component analysis. So let me go ahead and start sharing my screen and we'll get right into it. We'll waste no time. Okay, and just kind of reminder again, like, I think we went through dimensionality and then PCA, like talking about like what PCA is. And again, I mentioned that a lot of times PCA, even though it's like it is an unsupervised learning algorithm, it usually is considered kind of like a pre-processing step. So I just kind of know that is kind of like a lot of the steps you can do. There's some interesting things you can do with it as well. PCA can do things like ignore noise and stuff like that too. So one kind of interesting application is something I think they showed in the curriculum, like eigenfaces, where they kind of show you how to do like facial recognition with PCA essentially. And basically it's saying that it's finding like the vectors that basically are like, oh, these are kind of common faces. Something similar can also be done with like written words, like with MNIST. So it's kind of a really cool way to kind of apply it. But let's kind of see a little bit example. So I wrote this little notebook together. And so the first thing we want to do basically is just create a data set. And so I'm going to use the good old iris data set. Actually, it looks like I don't have this kernel reset. So let me make sure I have this kernel reset so we don't get any weird stuff. You can see like this line 16 means I ran it before and I checked the kernel. But we'll load in the iris data set. And then once we load in the iris data set, we'll go ahead, classic stuff, right? I'll go ahead and scale it just to make it a little bit easier for us to deal with. If I look at it now, for example, if I check out X right here, it's a standard scalar. So it's going to shrink it down where basically that mean is going to be at 0. And then we have a standard deviation of 1, right? So nice and easy. And then we'll go ahead and plot this out so you can kind of see what this part is. And one thing I did here is basically, we're looking at 2 dimensions. So remember that this is dimension of 4, right? So we have 1, 2, 3, 4 columns, and the class is going to be represented by color. So that's really our target here. And so there's not a real way for us to write 4 dimensions, but we can imagine taking like slices of it, like in these 4 dimensions. So basically 2 features at a time. So you can see here, basically I'm plotting all the 2 different features. And you can see some of the combination of features do better in separating the values over others. For example, petal length looks pretty good in the sense that like if we travel down this diagonal line, petal length versus petal width, you can see like as we travel along this diagonal line, essentially we start seeing a different color. So this is actually be a really great candidate to like, decide on here. But if you look something like at sepal length versus sepal width, there is some distinction between here, but looks like the green and blue classes, which I can't remember which are which, but these are going to look very similar to each other. It's not a direct way to linearly, separate these 2. Okay. So this kind of shows like, what we do with PCA. So remember, PCA is going to combine these different, these 4 different features together to create kind of like a super feature essentially. And what's kind of cool, we can actually say, hey, only do so many principal components. It can actually calculate all of them, like, like we talked about, like the max number it would have with like the number of features it has. So the most it would have is 4 here. We can actually say, hey, let me just do like the first 2 or a certain percentage. So using scikit-learn's PCA implementation, you can see here we got a decomposition, right? So we can kind of like imagine like decompose like the data set into like a certain number of components. Here I just put, for example, you could say % of features. So note that in the documentation, this n components can take either an integer, which will be just the number of features, or it can take a float between 0, well, I guess above 0 and below up to 1. And that represents percentage. So basically you can say, oh, if you have like, let's say 100 features, you can say, give me the first, like 10% of them, or the first 75%, or whatever you want. Or you can specify how many features in total. And it'll always give you the most important ones, and the least, then start going down as it goes into the least important ones. Okay, and remember, how do we measure importance with PCA? Like what defines it to be more important over another component?
The amount of the variance it can explain.
That's right, yeah. The more variance along that component, the more important it is, right? Basically, it just means that there's more information to be had on that one component, okay? So we'll go ahead and use, in this case, just we'll use two features. So notice this is not going to do anything before. And so now we have PCA here. Remember, PCA here is actually an object. So we can actually call our .fit transform. So I will talk about this, especially in pipelines, I think, which will be tomorrow. But know basically that this is the equivalent of calling PCA.fit with X and then PCA.transform. And what's happening here, it basically is fitting based on this data. It's trying to figure out what the components are in the from the data set X, and then it's going to transform this part right here. Well, this is going to return the transformed X based on whatever it fit. But this is kind of a quick way to just put it in all at once. In fact, this tends to be a lot more efficient, if not the same as calling fit and then transform. Okay, so I'm just saving this X transform as a separate kind of like variable so I don't get it confused with X. A lot of times you just replace this with X by itself, but I'm just calling it transform to make it clear that this is the transformed data. Okay. So once I do this, we can actually kind of check this out. What's a really nice thing you can do is essentially just add a new features on here. And so you can see here is that I'll actually create a new data frame here. And you can see here is that this is the transform data. And this right here is based on the, oops, I misspelled some of these things. Should probably PCA1, PCA2 like this. That makes more sense. You can see here, basically, this is the first axis, the first component, and then this is the second component. And each of these points are those original data points that are transformed onto this axis. So you can imagine, like, if I go back to like the very first point right here, this point right here with this certain sepal length, sepal width, and so on, it's been basically mapped onto these two axes, PCA1, PCA2, with these values. Okay. So this point still exists, it's just kind of been projected onto a different figure. So we can actually check this out, what it looks like. So in this case, I'm going to take this information now and plot it out and see how it's explained. So remember, I took all combinations that we could possibly do of different axes. And note that I could swap X and Y. It wouldn't really matter. It looked the same. It just kind of flipped on the Y equals X line. But you can kind of see like what would be most separable or what can be explained. So we're hoping to see PCA to basically be at least just as good. And you can see here is that's pretty decent where we can get more or less all the information in this. And that's what PCA determined, that this is the best two axes to basically represent that information. So more or less you can kind of see is that most of the information is probably on this PCA1. Basically most are red are on this kind of like -3 to -2. The green is about 0 to 1. And then from 1 to 3, it's blue. And then obviously there's some kind of overlap, right? Because we noticed that green and blue tended to be very similar to each other. And some of that explanation can be explained with PCA, the second component right here. So basically the idea is that most of the combination of this part can mostly explain these things. If we get basically all of those three, PCA 3 and 4, we would have the same amount of information as we had started off with. Okay, cool. Makes sense to everyone? Any questions? Pretty good, yeah, cool. So this is a way you could basically feed this into now your machine learning algorithm to help separate it, versus you can see here, it's that you would have to try to figure out what maybe if you were only going to use 2 features, you'd have to do a whole lot to try to figure out what would be the best ones to kind of explain here. And note that I mentioned like this one probably is a really good candidate, maybe even like this top one right here. But this also relies on the fact that you have you still have 2 features in here. And then you can kind of see is that you can probably imagine that PCA 1 more or less might be actually following along this line. So if you imagine like a line drawn this way, that's kind of like what's going on here. If we were to kind of like draw it on there, it's basically saying as you increase in that line diagonally, you'd get just red, then mostly green, and then mostly blue. So hopefully you guys can kind of see that relationship if I drew that line. Okay, cool. I did have another visualization. I can't actually remember exactly what I did, but I took the same data, I think. I just showing in a different way, I think. Let's see here, components, X iris, going to the same thing. In this way, I think I was showing a different visualization. Oh, so I can go ahead and plot. This is just using Seaborn instead. And you can see here is that it's, again, comes up with the same information here. It's just a different way to plot it with this LM plot from Seaborn. But one thing I did want to show is this explained variance. So what's really cool is that PCA will actually say how much variance was actually explained. And you can see it's basically ranking the first PCA component is going to have the most variance, and then the second one, third one. I could actually change this like 3, or let's say, or we'll just go ahead and do, what happens if I get rid of n components? What does PCA end up doing? Does anyone know? Anyone got a guess?
Doesn't it? Doesn't it use all the features?
Yeah, we use all the features, which makes sense, right? So you can see there's 4 features in this case. So you can see here, basically, these first 2 have the most explained variance, right? So you can imagine, like, if you wanted to do this for a PCA, where maybe you say, okay, I don't know how many components I really want to keep. You can do PCA and you can say, okay, like going through this part, like, okay, it looks like variance drops off significantly after a certain point. Let me go ahead and cut it off right there, since basically this is kind of like where the most information is. And you can see by keeping the first 2, we get the most explained variance. There might be some advantage to keep the third one, but there's not necessarily needed. You can also do this dot component. So note that the explained variance with this underscore and this exponents with an underscore, those are basically attributes of the object itself. So they're little properties essentially of that object. And note that scikit-learn is actually really consistent whenever you have a object like this. So you can see like PCA, I don't know, I have this twice. But if you have like this object here, right? Want to access some of those extra like, properties and stuff, you just basically have it defined here, and this always ends with an underscore. Okay, so these PCA components will actually show you what the vectors are, and this is what's really cool. Anyone got to guess what, why there are 4 components and it's like this? Like, what are these things representing, you think? Let's try to hit. So this was 4 of them, right? So let's go ahead and see if I just copy these 2. I'm going to try to do 2 components this time, right? Oops. So we do 2 components. You can see those are the 2 most common ones. I'm going to do PCA this one. You can see there's still 2 rows here, each of these components. But why do we have 4 columns in this case for both of these? What do you think those columns represent?
Oh, aren't they the largest of the array above? Like the 2 largest. So the first and the second one.
I think when you say largest, you mean the best like component for like largest variance?
Yeah, like the best. So, well, the first one came, I don't know.
Okay, I think
Yeah,
you're
like
definitely right in the sense
best.
that. What's that?
The 2 best, I guess.
Yeah, so these rows are going to each represent each component. So this is the best component here, the first component, right? The second component, right? So these are representing the components in some way, but like we're trying to figure out like why these numbers come up, like not exactly like how to define them.
Are
Jenny might...
they kind of like coefficients for each of the variables? Like if you took each variable and multiplied it by one of those, you end up like shifting to make the component?
Yeah, so what's going on here is basically, I think, Jen, you pretty much have it right there. I would actually call them more like vectors. So if you remember, this is a vector right here. And this is basically, this vector is representing if you were to take the original 4 features. So feature 1, feature 2, feature 3, and feature 4 before the PCA, and drew a dot at 0.52 on the first feature, negative 0.269, on the second feature, and so on, and then draw a line in that direction, that would be a vector. And that's actually, that vector points in the direction of the principal component. So that would be like the new axis. So you can kind of think of this being like the guide of saying, how do you translate between the old features to like the new principal components itself. So this is why you'll have 4 features. If we only had 3 features, if we had 10 features, this would be a 10-dimensional vector, if that makes sense. So I just wanted to point this out. That basically this information is still there. So if I had what I could do, for example, if I were to plot out the vector here in like, these parts right here, you would see the vector come out like in a certain direction, and you would see that's where the PCA is going through. I wish I could kind of quickly do this, but in my head. But if you imagine 0 and 1 here, I think the first one was like 0.05. It's like basically pointing out in this direction. So you would be able to plot out this little vector and say, oh, that's what direction it's going in. And you can do that for each of these parts. Maybe that's something I could do in the future, but I won't fiddle with it right now. But I just wanted to show you guys that you can technically take these principal components and actually plot them onto the original features. Okay. Cool. All right. So Or actually, you know what? I'm going to quickly, I do want to show you guys that. So I'm just going to draw it by hand versus like coding it in. So let's see, pedal wing. Yeah, so this is the first one, the second one, the third one. So this is the third one, 0, 3. So you guys are going to have to help me out here, maybe. So this is the first component. And we're going to do this value and this value. So 0.52, 0.58. And we're going to draw it on this graph right here. So if you imagine, I'm just going to draw it in brown. 0.58, I said, or 0.52 is the very first one. So, well, it's not going to help very much, but you can imagine 0.52 and 0.58 would be like right about here. So it would be something like this right here. Basically, the first component is pointing in this direction where it looks like, if I were to kind of draw it out, it would look something like this, which makes a lot of sense. That's kind of what we saw right here. And then if we were to do this like on this very last one, which is the second one in third component, so I'm going to scroll down a little bit. The second and third component. So this would be the second component. And oh wait, I have this backwards on it. This should be the second component. This should be the third component. So this would be 0.58, 0.56 would be right here, 0.5. So basically it'd be something like around something like this. Is that first component if you were to plot this on top of there. So that kind of makes sense in the sense like, oh, we would expect it to be like this. And then these points are projected down onto that first component. Okay. Hopefully that's not too confusing, but at least maybe we'll show another time where it's possible. Okay. Any questions you guys have on PCA before we move on? Pretty good. Okay, cool. So I'll go stop recording here and we'll move on to clustering.